Alright, so in this video we're going to talk about strain energy due to transverse loading of beams. So what we mean by transverse loading is if we have a force that's applied perpendicular to the length of a beam, what that force does is it creates two stresses. It creates a shear stress tau xy and a stress sigma x. Okay, so both of these are going to be functions of x and y along the beam, but they're not functions of the depth of the beam. They're not functions of z. So we don't have to worry about that. So we can define our volume element dv as being dx times dA, where dx is here and then dA is here. Okay, so if we look at this element here, we know that basically that this element will be under plane stress, so there's no stress in the z-axis or in the or along the z direction. So our stress element looks like this. All right. We can also say that there's no stress being applied along the y-axis, so we can say that sigma y is going to be equal to 0. In this case for transverse loadings. So we can say that our total strain energy due to transverse loading would be equal to the shear strain due to the strain energy per unit volume times dV, and we have to integrate it across the whole volume of our element here. So if we plug in that sigma y is equal to 0 into this equation, what we'll end up getting is and we distribute the differential volume within the integral, we can end up getting two equations. We'll get one equation that's just a function of a function of sigma x, and one equation that's just a function of tau xy. So we'll get our bending stress and our strain energy due to bending and our strain energy due to shear. So we're going to separate out these two strain energies separately. So we're first going to start with the bending strain energy. So we can set that that sigma x is going to be equal to this minus mzy over iz, and we can recall that iz is going to be equal to the integral of y squared dA. If we plug all that in, what we end up getting is that our total bending strain energy is going to be equal to 1/2 E divided by iz mz squared dx. Okay, so so if the elastic modulus and if the Poisson, so it's the same material, and if the beam has a constant cross section, we end up, so these are constants. If E and I are constant, we can then simplify this equation down even more, and we'll end up getting just the following equation for the bending stress, where we only have to evaluate the integral as a function of z, or the integral about the z-axis squared times dx. Okay, so we can make the substitution that the moment as a function of z is equal to eiz times the second derivative of the displacement of the centroid of our beam as a function of y with respect to x squared. So if we make that substitution here, we can rewrite the bending stress in terms of this case. All right. So either of these two is fine to use. It just depends if you already know what VC of x is equal to. You can use this equation. If you don't, you can use the moment as a function of z. All right. So it just depends on which one is easier to evaluate. All right. So the next thing we need to do is we need to evaluate what the shear energy is equal to. So earlier we defined our shear strain energy is being equal to this term, we're going to substitute in tau xy is going to be equal to VQ over IB. So if we do all that, and we rearrange a few things in terms of what dV is equal to, what we end up getting is that our shear strain is going to be equal to this K term, which is a correction factor for shear, over 1 plus the Poisson's ratio divided by EA times the shear force squared dx. That K constant is going to depend on the type of cross section that's being used in the beam. So for a rectangle, for example, it's 1.2. For a circle, it's 1.11. For I-beams and other sections, it'll be 1.0. And then for hollow tubing sections, it would be hollow round tube, it would be 2.0. So if you don't know what the K constant is, you can assume that K is going to be equal to 1. All right. In a lot of cases, also you can assume that the Poisson's ratio and your elastic modulus are constant if it's the same material across the whole beam, and if you have a uniform cross section across the whole beam, that equation for the total shear stress, the total shear strain, total strain energy due to shear would simplify down to this nice simple equation here. Okay, so typically the bending stress is going to be is much greater in shear unless you have a very short beam. And again, just to remind you, is that the total strain energy is just going to be equal to U bending plus U shear in the case of transverse loading. All right. So in the next video, we're going to do an example problem that will be used to calculate U of bending and U of shear. The shear strain, the strain energy due to bending, and the strain energy due to shear.